Welcome back. I have a structure here that is in equilibrium. It's a bent rod. You can neglect its weight. It's subject to a downward force of 100 newtons and a clockwise 20 newton meter couple moment. You can see all the relevant dimensions in the image. The support at point A is called a fixed member connected to collar on smooth rod. So you have a member here that is fixed to a collar, and that collar can slide along this smooth rod. And now it's important to understand that the collar is fixed to the member, meaning that it is welded to the member. And then at point B, you have a support called smooth contacting surface. If we neglect friction between this member and the ground, then this member can move along the surface. Also note that it's not fixed nor connected to the ground in any way. You simply put the member on the ground and you leave it there. And now your task is to identify and find the reactions at points A and B. Good luck. Give it a shot by yourself first and then see the solutions in the next video. Thank you. Welcome back. Let's now identify and find the reactions at point A and B. Let's first take point A. You have a smooth rod and then the collar can slide along that rod. So translational motion along the rod is not restricted. However, translational motion normal to the rod is restricted, which means that there is a reaction force applied to the structure normal to the smooth rod. But it's not the only thing. Note that the member itself is welded to the collar. It means that rotational motion about point A is also restricted. So you also have a reaction moment there. There is another type of support where the member is connected to the collar with a pin. In that case, the collar can still translate along the rod, but in addition, the member can rotate about this pin A. In that case, there is no reaction moment in this location. You only have a reaction force A applied normal to the rod. But that's not our case. In our case, the member is welded to the collar, thus you have a reaction force normal to the rod and you have a reaction moment. So they are both applied to the member. What about point B? Well, at point B, the member simply lies on the ground. There is no restriction to rotation about point B, and assuming negligible friction between the ground and the member can also translate along the ground. Only motion perpendicular to the ground is restricted. Thus, you only have one reaction force, which is normal to the ground. This is the force that the ground applies to the member. And now, you only have to draw the free body diagram to this object and apply the rigid body equilibrium principle to find your reaction forces and moments. So let's do it here. These are my positive x and y axes. And now, in addition to this 100 Newton force and this 20 Newton meter couple moment, I'm going to put this reaction force B here, which is 90 degrees to the ground. And so if I say that this angle here is phi, then that means that also this angle here, it's also phi. And then at point A, I will have a reaction moment, MA, and the reaction force, A, perpendicular to the rod. And now, if I say that this angle here is theta, then that also means that this angle here is theta. And so this is the free body diagram. You can see the theta and the phi angles. The two theta angles are the same because the A force is perpendicular to the smooth rod, and the two phi angles are the same because force B is perpendicular to the ground. You can see the directions of the rod and the ground with those right triangles. And so now we can easily say that cosine theta equals 4/5, sine theta 3/5, cosine phi 12/13, sine phi 5/13. And now you can use all this to decompose your A and B vectors when you apply the rigid body equilibrium principle to this free body diagram. And so let's do it. Forces in the x direction, they give me ax minus bx, which I can write like this or like this, and that will be 0. Then forces in the y direction, it will give me this equation, and then I'm just gonna take moments about point B. I have my reaction force MA, which is here, minus the couple moment that I have here. Then this is the moment due to AX, due to AY, and then due to 100 newtons, and all that must be 0. In other words, I can rewrite this equation like this. My AX is A cosine theta, but you know your cosine theta, which is 4/5. That's why you have 4/5 here. And the same thing with AY, it's A times sine theta, and your sine theta is 3/5. That's why you have 3/5 here. And you can do the same thing with BX and BY. BX is B times sine phi, and then your sine phi is 5/13, and then BY is B times cosine phi, and so you can replace cosine phi with 12/13. And so from the first equation, you have this result. So A equals B times all this. In other words, A equals 25/52 times B. And now in the second equation, instead of A, you can write this thing here. You can substitute A with this, 25/52 times B. Then your second equation becomes like this, where you have 63/52 times B, and that equals 100. So your B equals 100 times 52/63. Then you have 5,200/63 newtons, which is approximately 82.5 newtons. And then right away you can calculate your A. It's 25/52, and then instead of B you have this number, and as a result this is your A, which is approximately 39.7 newtons. And so you have your A force, your B force, and now you have to find your MA. So you simply need to rearrange this final equation. If you do that, then you will have MA equals, and then all this, which is 670/63 Newton meters, or approximately 10.6 Newton meters. And there you go. You have the reaction forces and moments. They're all positive. That means that your initial assumption about their directions was correct. Thank you. Welcome back. I have a platform assembly here that rests on two wheels at C and D. The weight of the assembly is 1000 newtons, and its CG is at G1. It also has a carrying platform. The maximum weight of the entire platform with all the load inside it is 1600 newtons, and the center of gravity of that platform is at G2. Then at point B, you have counterweight blocks with uniform mass distribution. All the relevant dimensions are in the image, and my question to you is very simple. What is the smallest weight of the counterweight blocks that should be placed at point B so that the platform would not tip over? So these blocks, they are not part of 1000 newtons. So what is the minimum amount of blocks in terms of weight, in terms of newtons, that you need to put here so that this entire thing would not fall over? So try it out by yourself first and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the minimum weight for the counterweight blocks to prevent this entire thing from tipping over. We can start by drawing our free body diagram. You have Fg1 and Fg2 that are known. Here are the positive x and y axis. Then remember that the entire structure rests on two wheels, C and D. These wheel supports give you resistance to translation perpendicular to the ground only. So you have forces NC and ND, and they are normal to the ground in the positive y direction. Now, of course, you might argue that there should also be reaction forces in the x direction, because due to friction, wheels normally don't go sideways. However, you cannot count on it. It depends on the wheels and the surface. What if you are on the ice? Then it would be easy to slide the structure laterally in the x direction. So it's simply better to assume no friction at all and design the whole thing without horizontal reaction forces, just to be safe. Finally, at points where the wheels touch the ground, the structure can rotate about those points, which essentially is when it tips over, something that we want to avoid with counterweight blocks. Thus, there are no reaction moments in the supports at C and D. You only have two normal forces, NC and ND. Finally, you have Fgb, which is the force of gravity of the counterweight blocks. Since their mass distribution is uniform, we know that Fgb goes vertically through the middle of the blocks. You have equal horizontal distance on both sides. In this case, it's not important to know the vertical location of the center of gravity for those blocks, because Fgb tries to prevent tipping over at point D by applying a counterclockwise moment about that point. Since Fgb only points down, you only have a moment arm that goes from Fgb till point D horizontally. And so, if you don't have enough blocks at B, then Fg2 might cause the platform to tip over at point D due to a clockwise moment about that point. Fg1 would counter that a bit by providing a counterclockwise moment about that point, but it would not be enough. Now here's the thing. To find the smallest Fgb that you need to keep it stable, the sum of the moments about point D needs to be 0 Newton meters. So the sum of the moments about point D will give you this equation. If your Fgb is the smallest allowed force, then the wheel at point C is about to detach from the ground. So there is no normal force there. Thus, this term here is 0. The wheel C is about to leave the ground. That means that you have one equation and one unknown. So I can rewrite this entire equation like this. In other words, this 3.5, I can put it here in the denominator. I know my Fg2, it's 1600 newtons, and FG1 it's 1000 newtons, and so that means that the minimum allowed FGB is this number, or approximately 314.3 newtons. And there you go, this is your answer. That's the minimum force you need to have to keep the structure in place. Of course, in reality, you should put more counterweight blocks in this location at B in order to make sure that it's secure. Also, when you divide 2200 by 7, then this is the real answer, but in these kind of problems, just to be safe, you should always round up. Because if you round down, then even when you have a perfect condition, your structure will tip over. Thank you very much. Welcome back. I have a platform here that is fixed to the ground, and then you have a 30-degree inclination here, and then on top of that, you have this big wheel. This wheel is connected to this member here, AB, with a pin. The other side of the member is connected to another platform that is fixed to the wall. You also have a spring here. The spring constant is 40 newtons over meter, and the spring is compressed. That's why you see S equals minus 0.2 meters. So it's not in tension, it's compressed. And so, like mentioned before, you have two pins here at A and B. And now, if pin A can withstand maximum load of 4 newtons and pin B a maximum load of 7 newtons, will any of those pins break in this configuration? The system is in equilibrium. You can neglect the weight of the wheel and the AB member. You have your spring constant. You know how much it's compressed. You have the dimensions here. Will any of these two pins break? Try it out by yourself first and then see the solutions in the next video. Thank you. Welcome back. Let's now find out if our pins at points A and B are strong enough. For that, in our minds, we will disassemble the structure and only focus on the AB member. And so we can draw a free body diagram to it. You can see that you have a roller support here. At B, that means that you only have a reaction force normal to the surface at this point. And this is also transferred to the AB member at point B. Since the inclination here is 30 degrees, that means that you have 30 degrees here as well with this vertical dotted line. On the other side, you have the reaction forces AX and AY at point A. And so I will also draw it here, AX and AY. Finally, you have the spring force that points down because the spring is compressed. And so this Fs, it will also be applied here at this point. Now we know the K for the spring and how much it's compressed. So we can already say that Fs equals K times the absolute value of S. At this point, I don't care about the direction of this force. I will care about it when I start writing the equilibrium equations. But for now, I will have 40 newtons over meter times 0.2 meters. The meters get cancelled out. And so I will have 8 newtons for my spring force. Because of the fact that the member AB is in equilibrium, we can apply the rigid body equilibrium principles to find the rest of the forces, AX, AY, and B. So this is the equation for the forces in the X direction, in the Y direction, and then I will take the moments about point A, and in the end I will have this equation where BY is B times cosine 30 degrees, BX is B times sine 30 degrees. This here is 275. Fs was 8. Also here, Fs was 8. Note that since the moment arms are in millimeters, the units for the moments have to be in newtons times millimeters. Also, I chose to take moments about point A because now I only have one unknown in my third equation, which is B. And so from the third equation, I have B times all this equals 150 times 8. And so B equals 150 times 8 divided by all this, and it's approximately 6.378 newtons. Then, from the second and the first equations, I have AY equals 8 minus B times cosine 30 degrees. You know your B, and so your AY is 2.48 newtons. Then your AX equals B times sine 30 degrees. Again, you know your B, so AX equals 3.19 newtons. And now the resultant A vector magnitude is A equals AX squared plus AY squared, and it's going to be all this, which will give you 4.04 newtons. The maximum loads that pins A and B could carry were the following. A max was 4 newtons, and then B max was 7 newtons. So you can see that B is less than B max, but A is greater than A max. So pin at A would break. Therefore, you need a stronger pin there. Welcome back. What I want to do now, I want to take this entire structure and disassemble it, and I want you to see that when this structure is in equilibrium, how exactly the forces get transmitted through this mechanism. Here you see the Newton's third law at play. We assume that the surface that the wheel rests upon is solidly fixed, and the same thing can be said about this part here that is fixed to the wall. Let it be our fixed plate. Of course, this fixed plate and this ground here, they have their reactions that a fixed support would have, but we don't care what they are. We just know that they keep the surface for the wheel and the fixed plate at rest. Our world starts with this diagonal surface and ends with this fixed plate. Now this diagonal surface applies force B to this wheel. That's from this surface. Due to Newton's third law, the wheel applies force B to the surface in the opposite direction. This wheel then transfers this force B to this pin B, that is the pin that connects the wheel with this AB member at this point B. Again, due to Newton's third law, pin B applies force B to the wheel in the opposite direction. Both B forces for the wheel get cancelled. That's why the wheel is at rest. The net B force equals 0 newtons. Pin B then transfers this B force to this AB member. And of course, the AB member returns the favor because of the Newton's third law. From the AB member, pin B has force B in the other direction too. The net effect is 0 newtons, and pin B stays at rest. The AB member receives the B force from pin B. Because of that, it will apply force Fs to the spring, and also to pin A, and here we're gonna draw this force using two components. So this is from AB member. Again, both the spring and pin A, they return the favor. Pin A applies the opposite AX and AY forces to member AB at point A, and then the spring applies Fs to the AB member. Then the spring and pin A apply the Fs and AX and AY forces to the fixed plate, and the fixed plate, of course, returns the favor due to Newton's third law. It applies Fs to the spring and to pin A. Here you have AX and AY, and now this is from fixed plate. Thus, pin A and the spring are also in equilibrium. The AB member also ends up being in equilibrium due to the forces of B, Fs, AX, and AY. Also, the diagonal surface and the fixed plate are in equilibrium because of the reaction forces and moments that are generated there. Because of the fact that the mechanism is not moving, all the components, if you look at them separately, they will end up being in equilibrium. They have to be. If they are not, then they would start moving, which is impossible when nothing is moving. So when your structure consists of several members, like this one, and it's not moving, then you can disassemble this structure in your mind like this and apply Newton's third law. Of course, you might now ask why a pen would fail if it's in equilibrium and the net force is 0 newtons. Well, consider this case. Your pen here, let's say that it has a force here, and then here and here you have F over 2 and F over 2, and then due to Newton's third law, you have the opposite F over 2 forces in this direction, and so you have this distance d over 2 meters here and d over 2 meters here. So all the forces and moments are balanced out here. So in the world of statics, everything is fine. But of course, in reality, this pen is made of some kind of material, and this material has limits. In non-rigid mechanics, you will learn that this configuration introduces bending moments that would try to bend this pin, and shear stresses that can just outright break the pin. Both cases, bending and failure due to shear stress or their combination, is very bad and must not happen. That's why your pin needs to be strong enough so that these failures would not occur. Of course, the pin would always bend a bit and you would always have a bit of dislocation, but for as long as it's so small and negligible that you can have a rigid body assumption, and for as long as it's elastic, meaning that if you get rid of this force, which means that the reaction forces would also disappear, then the pin would take its initial shape. For as long as you have that, you'll be fine. Thank you very much. Welcome back. I have a standing airplane here. It has unequal distribution of fuel in the wing tanks. The center of gravity of the fuselage is this point here, A. From the origin of this coordinate frame, the position vector of A is 2.1 times I plus 0 times J meters. And again, that's from the origin of the coordinate frame, which is O. Then this thing here is wing B, and its center of gravity is this point B, and so the position vector of this point from point O is this one. Then this is wing C. its center of gravity is point C, and so this is the position vector. The wheel underneath wing B is at point D, and so the position vector of point D is this one. And then the wheel underneath wing C, it's point E, and so this is its position vector. And finally, the wheel underneath the fuselage is this point F, and this is its position vector. Note that even though it's a 3D picture, we don't have the K component in our position vectors. That's because we don't need it in this exercise. And so, the weight of the fuselage is 225 kilonewtons. Then the weight of wing B, it's 40 kilonewtons. And then the weight of wing C, it's 30 kilonewtons. And so, my question to you is, what are the normal reactions of the wheels D, E, and F on the ground? Try it out by yourself first, and then see the solutions in the next video. Thank you. Welcome back. Let's now find the wheel reaction forces at points D, E, and F. We are now starting to deal with 3D rigid body equilibrium problems. In 2D, you had a 2D coordinate frame where essentially the z-axis pointed out of the screen towards you. Your rigid body equilibrium principles were the following. The sum of the forces in the x direction had to be 0, the same thing for the y direction, and then the sum of the moment about some kind of point P when you rotate about the z-axis, either counterclockwise or clockwise, that sum also had to be 0. So this one was in newtons, this one also, and this one was in Newton meters. And remember, this point P, it was a point of your choosing. And then rotation in this direction was positive because it was counterclockwise, and this one was negative because it was clockwise. So that's according to the right-hand rule that you learned in Statics Part 1. Now, even though you can choose this point P, you still have to exercise some judgment there and try to take that moment about a point that is more convenient, meaning that you want this third equation to have as little unknowns as possible. And so you ended up with 3 equations, and if you had 3 unknowns, you could solve for them. In 3D, the logic is the same. You start with a free body diagram, and then the sum of all the forces in all the directions, and then the sum of all the moments in all the directions, they all had to be 0. The only difference is that now you have more of them. You have to consider forces and moments in the x, y, and z directions. Your rigid body equilibrium principle is the following. The vector sum of all the forces needs to be a 0 vector, and the vector sum of all the moments needs to be a 0 vector. Or in other words, you can write it like this. You get 6 equations. If you have 6 unknowns, you can solve for them. In the free body diagram, you determine your positive x, y, and z directions for your forces and moments. And when it comes to rotation, then you have to use the right-hand rule, where you wrap your right-hand fingers about an x, y, or z axis, and so the direction that your right-hand thumb points to, that's the positive direction for your moments. If your right-hand thumb points in the negative x, y, z directions, then you have negative moments. And so, let's now apply all that to our airplane. Thank you very much. Welcome back. So let's now find the normal forces for D, E, and F. We start with our free body diagram. We draw the weight vectors for our fuselage and 2 wings, and all of them of course point down in the negative z direction. And then the three wheels that we have, their reaction forces are only normal to the surface. They all point in the positive z direction. We have our three weight vectors, and now we have to find our three normal forces, ND, NE, and NF. So the sum of the forces in the x direction, it has to be 0, and also in the y direction, but you have no forces in those directions. Thus, you can ignore these two conditions, but you have forces in the z direction. Thus, you have this equation here. You also have moments about the x and y axis. Using the position vectors that you see here and the right-hand rule, you can formulate those two equations like this. This is all the moments in the x direction. This is all the moments about the y direction. Note that this force here, WA, it does not produce moments about the x direction because there is no moment arm from that axis. That's why in this equation you don't see WA here. And then the wheels NE and ND, they don't produce moments about y because there are no moment arms from the y-axis. Also, note that all forces are parallel to the z-axis. Thus, you have no moments about the z-axis. So you can ignore this condition here. And now, you have three equations here, and you have three unknowns. Let's take the final equation. The only unknown here is NF. I can rewrite this equation like this, and so this 8.1, I'm gonna put it here. You know your WA, WC, and WB, so NF equals 1855 over 27 kilonewtons, which is approximately 68.7 kilonewtons. Then from this equation here, I can have this form or this form, and if I calculate that, then it will be 0. So ND minus NE equals 0, which means that ND equals NE. And then from the first equation, I can have it in this form. Then I can put this NF here and get rid of it here. Then NE is the same like ND. So I have 2 times ND equals all this. And then I take this 2 and I put it here in the denominator. And so my ND will be this thing or this thing. Since ND equals NE, then this is also my NE. And there you go. That's how you find the reaction forces for your 3 wheels using the 3D rigid body equilibrium principles. Thank you very much. Welcome back. I have an airplane wing here. Its jet engine gives you an 8 kilonewton force of thrust in the positive x direction. The wing also generates 45 kilonewtons of lift. In reality, the wing experiences upward lift distribution across the entire wing's top surface area. But let's say that we have integrated all that and we have found that equivalently you can represent it with a 45 kilonewton point force that goes through the center of pressure at point B, which is this point here. Similarly, your wing has a mass which is 2.1 megagrams. You can assume that G equals 9.81 meters per second squared. It means that the wing experiences force of gravity, which in reality is a downward force distribution per unit area in newtons over meters squared. But we assume that the gravity point force, Fg, goes through the center of gravity of the wing, which is here at point G. And so if I draw it, then it looks like this. It's going to be Fg equals 20.601 kilonewtons. And it goes through this point at G. You get this number if you take your mass and you multiply it by G and make the necessary unit conversions. And so you have all the relevant dimensions in the image. And now here's what we need to find out. At the location where the wing is connected to the fuselage, let's call this location point A. It's essentially the origin of your coordinate frame. At that location, we need to identify and find the reactions. So good luck. Try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now identify and find the reactions at A, where the wing meets the fuselage. Firstly, what I want to say is that in comparison to regular construction beams, during the flight, the airplane's wings bend upwards due to the lift force quite significantly. So if we want to model the wing as a beam, then you can do that, but just know that the rigid body assumption here is a bit less true due to the fact that the airplane's wings deform significantly more than regular construction beams in structures. That means that the results that we will get here in this exercise for the reactions at A will be a bit further away from reality. But we can still use rigid body equilibrium for this, if the goal is the first order approximation to get a general idea of the support reactions at A. To counter uncertainties, what we do in the aerospace industry, we apply something called a safety factor. In fact, it's applied everywhere in structural analysis. It means that if, for example, the safety factor is 1.5, then all that means is that we find out at which load the wing fails, in other words, breaks. Let's say that the wing breaks at Lmax equals 150 kilonewtons, and then we divide that by the safety factor, so 150 kilonewtons divided by 1.5, which is dimensionless, and then you get 100 kilonewtons. And that 100 kilonewtons is the maximum allowed load you can have. That's your worst case scenario. So you take your worst case scenario, 100 kilonewtons, you multiply it by 1.5, and only then your wing can break. If it breaks before that, for example at 149.9 kilonewtons, then you have to make the wing stronger. If you go on YouTube and you write Boeing 777 wing test, then you can watch this first video here, and in this video they test the wing of Boeing 777, and they say in the video that the goal is to make sure that the wing fails at 150% of the worst case scenario. So 150% of the worst case scenario, that's multiplying your worst case scenario by a safety factor of 1.5. And then the wing can break at this force or a little bit above that, but not below. If the wing breaks a little bit below that, then the wing has to be improved. Anyway, let's now use statics to find the reactions at point A. Let's start with a free body diagram. We have our force of gravity, our thrust force, and our lift force, we know what points they go through. And now, what kind of reactions do we have at point A? At point A, can the wing translate in the x, y, or z direction? No. Thus, you have reaction forces in all three directions, AX, AY, and AZ. Now, at point A, can the wing rotate about the x, y, or z axis? No, it can't. So you also have three reaction moments at A. You have mx, my, and mz. This is called fixed support in 3D. It's completely locked. You cannot translate in nor rotate about any direction. And so let's apply our rigid body equilibrium principle to find them all. Let's start with all the forces in the x direction. That's your equation. In other words, Ax equals minus thrust. So Ax equals minus 8 kilonewtons. Ax is negative, so in reality, it's opposite in direction. Then let's do all the forces in the y direction. So you have Ay equals 0. There are no external forces in the y direction, so Ay, being the only force in that direction, has to be 0. Then let's do all the forces in the z direction. That's your equation. Az equals Fg minus L, and that will give you minus 24.399 kilonewtons. Again, Az is negative, so it points down, not up. Now, what I will do, I will take all the moments about point A and first in the x direction. That way, Ax, Ay, and Az will not produce any moments. So that's the equation. For the lift, the moment arm is 15 meters, and for the gravity force, 5 meters. The lift gives you a moment about the x-axis in the positive direction and the force of gravity in the negative direction. So the reaction moment mx equals all this minus 571.995 kilonewton meters. Mx is negative, so that moment in reality is about the negative x-axis, opposite to our assumption. Then let's do all the moments about the y-axis. This would be the equation. So my equals 2.5 times thrust, because this 2.5 meters here, that's your moment arm, and your thrust is 8 kilonewtons. So your my will be 20 kilonewton meters. My is positive, so your initial assumption about its direction was correct. And finally, let's do it for the z direction. Mz minus 8 times t, it's 0. Mz equals 8 times t, it's 8 times 8, it's 64 kilonewton meters. Again, Mz is positive, so it's in the positive z direction. And there you go. You have your reactions for the wing at point A. Finally, what I want to mention is that My is also called torsion. In general, if you have a beam and you have a moment about the axis that goes through the beam along its length, then that moment is commonly also called torsion. Also, what I want to mention is that a common mistake in statics problems is that when you draw a free body diagram and you get a negative answer for your reactions, sometimes people tend to change the free body diagram. For example, if your mx points in the positive x direction on your free body diagram, but you find that it's a negative number, then sometimes people tend to redraw the free body diagram and put that moment mx vector in the negative x direction. But that's a mistake, it's very confusing. Your free body diagram should stay as it is, and if you have a negative number for your reactions, then you should just look at your original free body diagram and know in the back of your head that in reality, your moment vector has an opposite direction. Thank you very much. Welcome back. I have a sign here which is 100 kilograms. Its center of gravity is at point G. You can assume that the gravitational acceleration is 9.81 meters per second squared. You can ignore the weight of the AB rod and also the weights of the two cables that hold the entire structure in place. The support that you have at point A is called the ball and socket joint. Essentially, you have a socket in which you have a ball which is welded to some kind of member, and now this ball cannot leave the socket, but it can rotate inside the socket about any direction. So again, it cannot leave the socket, but it can rotate about any direction. So that should give you some ideas about the reactions for that support. And so your task is to identify and find the reactions at A. And also, I ask you to find the tension forces in cables BC and BD. All the relevant dimensions are in the image. So good luck. Try it out on your own first and then see the solutions in the next video. Thank you. Welcome back. So let's now identify and solve for the reactions at A and find the tensions in cables BC and BD. As mentioned before, we have a ball and socket joint at A. The ball cannot leave the socket, but it can rotate about any direction. It means that at point A, there are no moment reactions, but there are force reactions in all three directions. So you have AX, AY, and AZ. Then at point B, you have two forces, FBC and FBD, and they point towards C and D respectively. And of course, the lines of action of these two forces are along the cables. Finally, we have the force of gravity of the sign, which is m times g, or simply 981 newtons. Let's now decompose the forces FBC and FBD. We need a displacement vector from B to C and from B to D. I'm simply following the procedure that you learned from Statics Part 1. So RBC equals this vector, then RBD equals this vector. You literally walk from B to C and then from B to D first along the X dimension, then along the Y dimension, and then along the Z dimension. Then you need the magnitudes of these two vectors. The magnitude of RBC is 3 meters, and the magnitude of RBD, that's also 3 meters. Then the general unit vectors from B to C and from B to D are the following. This is UBC and this is UBD, and they are both unitless. And now, to decompose FBC and FBD, you do the following. Vector FBC equals the magnitude of FBC times the unit vector UBC, and then FBD equals the magnitude of FBD times the general unit vector in that same direction. This is the FBC vector, this is the FBD vector. Now you have these two forces in the Y, J, and K components, and now let's use the rigid body equilibrium principles to find AX, AY, and AZ, and also FBC and FBD. In the X direction, in terms of forces, you have this equation. In the Y direction, in terms of forces, you have this equation. In the Z direction, in terms of forces, you have this equation. Then I'll now take the moments about point B. That way, forces FBC and FPD will produce no moments. So this is about the x-axis. Then there are actually no moments produced about the y-axis. And this is about the z-axis. From here you can see that AX equals 0/2, which is 0 newtons. Then from here you can see that AZ equals FG/2, so 981/2, 490.5 newtons. And now I will take my force equations and I will rewrite them like this. Or what I can do with the last equation, I can put 981 here and get rid of it from here. Then I can put here minus 490.5, and so this term goes away. I can just put here 0, and so here I can say that 981 minus 490.5, it equals 490.5. And now I can take these three equations and I can put them in this matrix vector form, where this one is an A matrix, this one an X vector, and this one a B vector. You can find the X vector like this. You take the inverse of your A matrix and you multiply it by this B vector. And in the previous course, in Statics Part 1, I simply recommended you to use some kind of inverse matrix calculator that you can easily find on Google, where you can simply type in your A matrix and it will give you inverse A. So this is my inverse A matrix times B, and that's your result. The first element is AY, 588.6 newtons. Then you have FBC, the tension in this cable from B to C, that's also 588.6 newtons. And then the final element is for FBD, that's the tension in this cable from B till D, and that's 294.3 newtons. And there you go. You have your reaction forces and the tension in the cables. Thank you very much. Welcome back. In this video, I would like to point out a couple of things. When we had a 2D equilibrium problem where we had to find the reaction forces and moments, we ended up with three conditions: the sum of the forces in the x direction, and also the sum of the forces in the y direction, and then the sum of the moments about some kind of point. They all had to equal 0. And thus we had three equations and at most three unknowns. And then you solved for the unknowns. Similarly, when you had a 3D equilibrium problem, then you had 6 conditions, 3 for the forces and 3 for the moments. Thus, 6 equations and at most 6 unknowns for which you could solve. However, sometimes you can have more unknowns than equations. Consider this case here. You have a fixed support at A, so for the reactions you have AX, AY, a reaction moment, MA, and then you have a roller at B and C. So you have BY here and CY here. And so you have 5 unknowns: AX, AY, MA, BY, and CY. But you can only have 3 equations for this system. And so this configuration is redundant. It means that you have more supports than needed. Redundancy is applied to make systems safer. But from a statics point of view, you don't need supports at B nor at C. You have a fixed support at A, and that will keep the beam in equilibrium. Of course, in reality, supports at B and C reduce loads at A. That's why it is used. But you can't solve for all the 5 unknowns using statics. It's called a statically indeterminate problem. A system like this can be solved if you remove the rigid body assumption and examine how the beam deforms. For example, in this case, you have 4 unknowns. You have AX, AY, MA, and BY. And the beam deforms something like that. If you know the material properties of your beam, then there are equations that give you the ability to solve for these 4 unknowns. This is part of mechanics of materials, which would be the next logical step after statics. After statics, you can essentially go in 2 directions: dynamics and mechanics of materials, which is essentially non-rigid structural analysis. And another thing that I want to mention is that when you create constraints for your structure, then you have to be careful. Consider this case here. You have a pin at A and a roller at B that is attached to a wall. And then you have this force P applied to the beam. And so here you would have reaction forces at A, then here at B, and you can already intuitively see that this is a bad combination. It will make the beam rotate about point A. Or consider this case where you have a beam on 2 rollers at A and B, and then force P, which is applied to the beam diagonally. So you will have AY here, BY here, and obviously your beam will translate sideways. So that's bad too. In this case, we say that you have improper constraints. It is important to avoid them to make sure that your constraints actually keep your structure in equilibrium. Thank you very much.